Welcome back to our channel. In this lesson, we'll derive derivatives of sine x, cos x, and tan x from first principle, and then use identities to get the derivatives of sec x, cosec x, and cot x. I'll go slowly, line by line, and explain each step. First of all, there are two fundamental limits which we need to all memorize. These two limits are the backbone of the first principles proof for sine and cosine. You may know them from geometry or series. I'll use them directly and I'll point out where they appear. So first of all, let's start with the derivative of sine x using first principle. Example 1. Differentiate y equal to sine x. The first thing we need to do is recall our definition of first principle. What did we say? What did we say in the first video on when we were talking about derivative differentiation using first principle? The derivative with respect to x of f of x using first principle is the limit as h tends to 0 of f of x plus h minus f of x, all that divided by h. So in this, our definition of first principle, we identify two separate terms which we need to calculate. We have f of x plus h, which we need to calculate, and f of x, which we already have. So from here, we can then say the derivative with respect to x of sine x is equal to the limit as h tends to 0 of sine of x plus h minus sine of x, all that divided by h. What do we do then? We need to simplify sine of x plus h. Using angle identities, we all know that the sine of x plus h is same thing as the sine of x times the cosine of h plus the cosine of x times the sine of h. What does this tell us? This tells us that our numerator sine x plus h minus sine x simplifies to sine x cos h plus cos x sine h minus sine x. When we look at these three terms, we notice that sine x is common on two of the terms. So we can then factorize sine x out for both terms. We have sine x into cos h for our first term and minus 1 for our second term plus cos x sine h. Dividing this term now by h, that is sine x plus h minus sine x, all divided by h, gives us sine x into cos h minus 1, all that divided by h, plus cos x sine h, all that divided by h. Now, applying the limit to both terms, we then have the limit as h tends to 0 of sine x plus h minus sine x, all divided by h, which gives us the limit as h tends to 0 of sine x into cos h minus 1 divided by h plus cos x sine h divided by h. We all know that limit is commutative. What does that mean? That means that we can attribute the limit to both terms separately. That is, limit as h tends to 0 of sine x into cos h minus 1 divided by h plus the limit as h tends to 0 of cos x sine h divided by h. What do we still remember on limits? Limits affect only the terms which are in term of its bounds h. So any term which is not in term of h can be considered as a constant in this limit. What does that tell us? That tells us that this sine x can be brought outside, giving us sine x times the limit as h tends to 0 of cos h minus 1 on h plus cos x times the limit as h tends to 0 of sine h on h. If we recall our fundamental principles, our fundamental limits as h tends to 0, which we recalled here in the beginning, we know that the limit as h tends to 0 of sine h on h gives us 1. So what does that mean? That means we can replace all of this by 1. We also know that the limit as h tends to 0 of cos h minus 1 on h gives us 0. What does that tell us? We can replace this term by 0. This simplifies this limit to sine x times 0 plus cos x times 1, which then gives us cos x. So what can we then conclude? We can conclude that the limit, that is therefore, the limit, therefore, the derivative with respect to x of sine x is equal to cos x. We enclose our solution. So let's move on. Let's attempt the derivative of cos x. Example 2. Differentiate y equal to cos x. Following the same steps and still using first principle, the first thing we still do is recall our formula for first principle. What does our formula for differentiation using first principle tells us? It tells us that the derivative with respect to x of a function f of x is equal to the limit as h tends to 0 of f of x plus h minus f of x, all that divided by h. So what does this tell us? This implies that the derivative with respect to x of cos x is equal to the limit as h tends to 0 of cos x plus h minus cos x divided by h. What do we do further? What do we do now like this? We calculate our term cos x plus h. Still using angle identities, we all know that cos x plus h is same thing as cos x cos h minus sine x sine h. What does that tell us? This tells us that our numerator can simplify to our numerator, which is cos x plus h minus cos x, can then simplify to cos x cos h minus sine x sine h minus cos x. Just like the previous question on sine x, we notice that cos x is common on two terms here. So we can factorize out cos x for both terms. This gives us cos x into cos h, minus 1 minus sine x sine h. Now let's calculate the complete term, that is dividing our numerator by our denominator, which is h. Cos x plus h minus cos x divided by h can then be written as cos x in bracket cos h minus 1 minus sine x sine h, all that divided by h. This then simplifies to cos x in bracket cos h minus 1 divided by h minus sine x in bracket sine h divided by h. What do we do then? We apply our limits on both sides. That is, the limit as h tends to 0 of cos x plus h minus cos x all divided by h is same as the limit as h tends to 0 of cos x in bracket cos h minus 1 on h minus sine x into sine h on h. Close our braces. Knowing that limit is commutative, we can then separate the limits. That is, the limit as h tends to 0 of cos x into cos or cos h minus 1 all over h. We close our limit minus the limit as h tends to 0 of sine x into sine h on h. We close our braces. We can then remove these terms cos x and cos x out of the limits. Why? Because these terms are not dependent on h. They are not dependent on the variable of the limit. That means they are invariable. They cannot change in this limit. So we can then take it out. That is cos x into the limit as h tends to 0, the bracket of cos h minus 1 on h minus sine x into the limit as h tends to 0 of sine h on h. If we recall our fundamental limit, what did our fundamental limit say? It says that the limit as h tends to 0 of sine h on h is 1, and the limit as h tends to 0 of cos h minus 1 on h is 0. So what do we do then? We replace these terms. This gives us 0 and this gives us 1. That means our question reduces to this times 0, cos x times 0 minus sine x times 1, which simplifies to minus sine x. So what can we then conclude at the end of this question? We can conclude that, so therefore, the derivative with respect to x of cos x gives us negative sine x. Okay, let's move on to our third question or our third example. Example 3. And what is our third example? Differentiate tan x. First of all, before we start this, I'm going to leave you guys some time to attempt this question. Attempt it on your own. Try and come out with your own sort of answers. But just let me give you guys a small hint. Tan x is equal to sine x on cos x, which is a quotient. So that's just a small hint. Attempt the question and put your answers in the comment below. So I'll assume each and every one of you guys have attempted the question. Let's start working. The first thing to identify, as we all said here, is that tan x is equal to sine x on cos x, which is a quotient, it's a fraction. And if you remember in our previous video, which was the quotient rule, it is a method of deriving or a method of differentiating functions which are fractions. That is, you have a numerator and a denominator. In this case, we have a numerator and we have a denominator. So what was the first step we took in order to differentiate such functions? Our first step was to identify our numerator f of x and our denominator g of x. So what is the first thing we do? We say let f of x, which is our numerator, be sine x, and g of x, which is our denominator, be cos x. After doing this, we recall our formula for the differentiation. The derivative with respect to x of f of x on g of x is bottom, or derivative of top, that is f prime of x times the bottom minus the top times the derivative of the bottom, all that divided by the square of the bottom. Another way to memorize this is bottom d top minus top d bottom, that is bottom d top minus top d bottom on bottom squared, where our bottom is the denominator and our top is the numerator. So from this equation, we notice that our terms which we don't yet have, that is f prime of x, or the derivative of our numerator, the derivative of our denominator, and the square root of our denominator. Those are three terms which we need to calculate before we can continue with the equation. So let's start with the first term. The derivative of our numerator, that is f prime of x, is equal to cos x. That is, let me write this clearly, which is the derivative with respect to x of sine x is cos x. We have already proven this using first principle in our first example above. Now moving to our second term, the derivative of our denominator, which is same as the derivative with respect to x of cos x, is negative sine x. So from this, we can then calculate our numerator, that is f prime of x gx minus f of x g prime of x. We can calculate this as, what is our f prime of x? Cos x. What is our g of x? Our g of x is cos x still, times cos x, minus what is our f of x? Sin x. And what is our g prime of x? Times negative sin x. This gives us cos squared x plus sin squared x. If we can still recall trigonometric identities, the sum of cos squared x and sin squared x gives us 1. That is, recalling trig identities, cos squared x plus sin squared x gives us 1. So this tells us that our numerator minus f of x g prime of x is equal to 1. We can then calculate our next term, which is the square root of our denominator. G of x squared is same thing as cos x squared, which is equal to cos squared x. Now calculating the complete term, that is our numerator divided by our denominator, we have f prime of x g of x minus f of x g prime of x, all that divided by the square root of our denominator, gives us 1 divided by cos squared x, which is same thing as 1 on cos x squared. Still recalling trigonometric identities, that is, recalling trig identities, 1 on cos x is same thing as the function sec x. So what does this tell us? This tells us that our whole function minus f of x g prime of x divided by g of x all that squared is equal to sec x squared. So what can we then conclude? We can then conclude that therefore the derivative with respect to x of tan x is equal to sec x all that squared, or sec squared x. We enclose or encase our answer. So in our next video, we are going to differentiate the functions sec x, cosec x, and cot x. Thank you for this video, and bye. See you in our next video.